Namaste everyone, my name is Deepak Saini. In this talk, I'll introduce you to DeepXML, which is a generic framework for deep extreme classification. You might have already heard Manik talk about extreme classification in a previous talk. The aim in extreme classification is to learn to predict for a given point the most relevant subset of categories or synonymously labels from an extremely large universe of labels. Extreme classification has opened up a new paradigm for ranking and recommendation problems by treating each item to be ranked or recommended as a separate label in a multi-label classifier. Now, many research groups in both academia and industry are publishing papers on the topic. Within Microsoft, our extreme classification algorithms have been successfully shipped to various products and have improved the key metrics such as user satisfaction, coverage, revenue, and so on. Extreme classification algorithms are now powering several components across all major markets. For example, extreme classification is being used to provide recommendations in text ads, product ads, rich ads, dynamic search advertising, and so on, apart from the personalized recommendations on Bing and also beyond Bing.com. This very second, extreme classification algorithms are serving hundreds of thousands of predictions in these applications, helping users around the globe be more productive. Many of these tech transfers have involved the DeepXML framework, which is a generic framework for deep extreme classification. Since extreme classification is one of the most computationally challenging problems out there, people were initially using traditional ML to come up with scalable and accurate classifiers on fixed features. However, the need to learn the features tuned for the extreme classification task was felt. Thus started the area of deep extreme classification, where algorithms have now started coming up to learn the features along with the classifiers. Algorithms like XML, CNN, MAC, Attention XML, etc. did come up from different groups, but many of these algorithms could not scale beyond a million labels. Those like MAC, which could scale beyond a million labels, required multi-GPU training over multiple days. And even after that, they were still less accurate than some of the fixed feature algorithms. And this is because learning features and classifiers jointly is not an easy task. And in order to motivate the DeepXML framework, let me highlight some of these challenges. Consider this naive architecture shown on the slide, where we have connected a feature extractor such as BERT to a classifier such as a fully connected output layer having 100 million labels. Fine-tuning BERT or similar feature extractors and performing the forward parse or doing gradient backprop through the fully connected layer can be computationally prohibitive. For example, even if it were to take us just 1 millisecond in order to evaluate a label output, making prediction on a single document would take a day, while training might take months. DeepXML addresses all of these challenges by decomposing the deep extreme classification task into four simpler subtasks or modules, each of which have training and prediction time only logarithmic in the number of labels. However, this decomposition is done intelligently to ensure that the accuracy is not compromised. If I were to give just a three-line gist of the DeepXML framework, it would be as follows. DeepXML first learns intermediate features on a simpler task in module 1 and freezes them. These fixed features are then used to subsample hardest to classify negative labels in module 2. The intermediate features are then fine-tuned in module 3 jointly with the classifier training in module 4 by utilizing the sampled negatives. DeepXML framework not only gives us a way of thinking about deep extreme classification and have a unified view of all the algorithms in the space like MAC, Attention XML, etc., but we can go one step further. In fact, to give an idea about the generality and efficacy of the DeepXML framework, it can be shown that these seemingly disparate algorithms, though not directly derived from the DeepXML framework, can also be made more accurate and scalable when recast into the DeepXML framework. Furthermore, since DeepXML is a modular and generic framework, we have been able to derive a family of scalable and accurate algorithms from the DeepXML framework. I will now describe each of the four modules in detail. The objective in the first module is to train intermediate feature Z by optimizing a non-extreme surrogate loss function. These intermediate features should have the following two properties. First, they should be accurate in the sense that had we optimized the chosen feature architecture directly on the extreme task, then the resulting features should not lie too far away from these intermediate features. And second, in order to ensure scalability, we should be able to learn the intermediate features in time order n d log L on a dataset with n documents, L labels, and where d-dimensional features are to be learned. Now, because DeepXML is a generic framework, we can choose any feature architecture that is suitable for our application, including a convolutional architecture, an attention-based architecture, or even ResNet if we are dealing with images. Once the intermediate features have been learned on the surrogate task, they are frozen and fed into module 2. In module 2, we leverage the observation that the training data contains only a logarithmic number of positive labels per document. So the high level idea in this module is to reduce the extreme classification task for each training document to a traditional task by selecting all of the positive labels for the document, but only its order log L hardest to classify negative labels. This can be achieved by leveraging a negative subsampling technique based on hashes, trees, or graphs that lies at the heart of every highly scalable extreme classifier based on fixed features. In the third module, we use transfer learning to fine-tune the intermediate feature z and learn the final feature z plus delta z. The idea in this module is to learn better features for the extreme classification task while still ensuring that the hardest to classify negative labels in the final feature space z plus delta z continue to lie within the label shortlist that we created in module 2. Now many techniques have been developed for transfer learning and all of those can be used as part of DeepXML. In the fourth module, we jointly train a classifier along with the final features in time order nd log L. One simplest option is to train one versus all classifiers on the log L shortlisted labels per data point, also referred to as one versus some classifier. But other classifiers such as tree-based classifiers could have also been used. Like I previously alluded to, varying the choices of the four modules in DeepXML leads us to a family of algorithms with varying trade-offs between accuracy and scalability. These algorithms like Aztec, Decaf, Galaxy, Eclair, and Siamese XML have been developed keeping different application scenarios in mind and have appeared in different conferences this year. Aztec was the first algorithm to utilize the DeepXML framework for efficient training, and the subsequent algorithms make better use of label metadata and correlations to make more and more accurate predictions. But let me focus on Aztec for the results. Let me first present the results on small to medium scale publicly available benchmark datasets to which other deep extreme classification algorithms could scale. Applications in these datasets range from predicting the categories and other Wikipedia pages relevant to a given Wikipedia page to recommending related products on Amazon. Compared to state-of-the-art deep extreme classifiers, Aztec can be up to 12% more accurate while being 5 to 30x faster to train on these benchmark datasets. Furthermore, apart from Aztec, none of the methods could make predictions in milliseconds on a CPU. Attention XML and XML CNN could not scale to the Amazon Titles 3 million dataset with around 2.5 million labels and 1.5 million training documents. Mac could scale to this dataset but required 40 hours to train, while Aztec could be trained in under 6 hours and at the same time was 10% more accurate than Mac. In fact, for internal applications, Aztec could be scaled to datasets having hundreds of millions of labels. Let me now present the results on an internal Bing Ads dataset for matching queries to advertiser bid phrases with more than 3 million labels and 21 million training documents. None of the other extreme classification algorithms could be trained on this dataset given 4 GPUs and a week, whereas Aztec can be trained on this dataset within 13 hours on a single GPU. When compared in propensity score precision metric, which rewards predicting rare labels comparatively more, Aztec was found to be 23% more accurate than state-of-the-art methods in production like BERT-based sequence-to-sequence, SimRank++, etc., which indicates that Aztec can perform particularly well on data-scarce tail labels. Furthermore, Aztec was deployed on Bing to perform A/B tests on live search engine traffic, where it led to a 1.5% gain in click yield and 7.2% increase in query coverage over an ensemble of leading IR, XML, generative, and graph-based techniques. In manual labeling by expert judges, Aztec was found to increase the fraction of good predictions by 20%. So as Marnik mentioned earlier, there are many different applications where algorithms derived from DeepXML can be used to personalize the recommendations. Our objective over here is to improve the overall user experience by showing the users more relevant and thus fewer ads. And Aztec has been shipped to various applications to provide hundreds of millions of users with personalized ads and query recommendations with significant gains in various user satisfaction metrics. Continuing on, since DeepXML is a generic framework, we have also applied it to the task of predicting Amazon categories given the product image. This required minimal changes and just the feature architecture was changed to Resonate 18. As you can see, this particular algorithm derived from the DeepXML framework yielded prediction accuracies 10% higher than Dismac, Parable, and Slice on pre-trained Resonate 18 features. To conclude, DeepXML is a scalable and accurate generic framework for deep extreme classification, which has given rise to a number of algorithms leading to both product impact and publications. Due to lack of time, I have covered only Aztec in the talk, but the code for all the algorithms is available publicly along with the different benchmark datasets. Thank you.